Bismillahirrahmanirrahim. Greetings. Zeno's paradox that we discussed in the previous lecture through a fairy tale story of the race between the hare and the tortoise was an example in our search for a motive behind the rigorous and abstract mathematical definition of limit. Now, in this lecture, we are going to go through another example for the same goal. And the purpose is to improve our intuition and also take away as much as we can abstraction from the definition. So let's get started, shall we? Now, I go through the so-called rigorous and abstract, in a sense, definition of limit, mathematical definition of limit one more time. But please, for the students that are taking the course for the first time in calculus, do not get discouraged. The definition is a little bit abstract, but once we finish, I'm repeating myself, and go through the related theorems and solve one or two problems, then this definition will be very appealing to you and very interesting, and hopefully that will be the case. Okay, now he says that limit of f of x as x approaches c is equal to L, which is a real number. This symbol represents if and only if for a given epsilon. That means epsilon will be arbitrary. There exists a delta positive, epsilon and delta both are positive, such that the distance between x and c, absolute value of x minus c less than delta greater than 0. Greater than 0 means x, the value of x cannot be equal to c. That's another way to say that abbreviation. Less than implies f of x minus L absolute value is less than delta. Now the concept of absolute value plays kind of good important part in this, that as I mentioned in the previous lecture, I'm going to put one or maybe 2 hours lecture only about the topic of absolute value. Okay, then let's go and start the main part of the lecture, if we may. Now, I have written it large enough, is visible. I have looked at the videos, it is readable, so I don't want to zoom it in and out for you. He says that f of x equal to x squared minus 4 over x minus 2, all right? And then we are after to see what is the limit of f of x as x approaches to 2. Now, we have heard that limit of quotient is quotient of the limits. That's what we have heard. So the limit of f of x over g of x equal to limit of f of x over limit of g of x. That's what we have heard. Now, limit as x approaches of 2 of these, according to what we say, is equal to the limit of numerator over limit of denominator. Limit of numerator is equal to what is equal to, as x approaches to 2, equal to 0. And limit of denominator as x approaches to 2 is also 0. Therefore, we end up with a 0 over 0, which is absurd. So we can conclude that limit does not exist in this case. And of course, we are going to go further to see if this is the case. But for a good, curious student, is not going to immediately jump to the conclusion that the limit does not exist. He tries other ways before he is fully convinced that the limit does not exist. So that's exactly what we do. Let's go now through another example and see what, excuse me, not another example, same example, but in a different approach. So this time we are going to approach it through the product instead of limit of quotient is quotient of limit. We are going to take the limit of product is product of the limits and see if we can come up with the same conclusion as we did in the previous one. Now, in x squared minus 4 over x minus 2, I wrote it in the product form. It's a junior high algebraic kind of manipulation. As 2 over 3 is same as 2 times 1/3. Okay, now our f of x will be x squared minus 4 times parenthesis 1 over x minus 2, and now we are using the product rule for the limit. Limit of product is product of the limits, so limit of I have written limit of f of x times g of x is limit of f of x times limit of g of x, and both of them are going the x approaching to the same number. In this case we put c. Now limit of x squared minus 4 as x approaches to 2 is 0. And limit of 1 over x minus 2 as x approaches 2 is in a sense infinity, because the denominator becomes extremely small and numerator is the same constant 1, and 1 divided by extremely small number approaches extremely large. We know that we have that much maturity. So we end up with the situation of 0 times 1 over 0. 1 over 0 is, some people they call it infinity, which is not in reality, because infinity is not really a number, but that's what they call. So if you are used to that, we can say 0 times infinity. And I don't know what 0 times infinity mean. I know what 0 is, but infinity is not a number. So I cannot say 0 times infinity is 0. So what is 0 times infinity is another absurd situation which came up previously, which is 0 over 0. So again, we come with this, with this kind of observation, again we come to the kind of feeling that the limit does not exist. But again, for the good, curious student, is not going to give up. He's going to approach it any other way to see if he is correct. And so far, his intuition tells him that limit does not exist. So we go to see if our intuition can be correct. So what is the next step to do that is give us more precise answer is to go through numerical method, which means giving number and see what's going on by making tables. Okay, now let me go through that one and see. Well, I have put this one here. Let me discuss about this one. And I've already mentioned one more time, I'm going through. And limit of x squared minus 4 as x approaches 2, this approaches 0. So the limit is 0. It's never will approaching, never reach 0. As the race that we had between the hare and tortoise, the hare will never catch the tortoise. That was the Zeno's paradox, which is, as I said, logically is perfectly acceptable. So here, the limit of that eventual can ever reach is 0. And the limit of that is equal to what? The limit of that as x approaches 0 increases, approaches infinity. So we end up with the situation of 0 times infinity. So there are 3 possibilities can come. So the product can be either 0, can be infinity, or can be a number. So far we end up with the impression that the limit does not exist. So let's continue and see if that is the case. Now I have another example. I don't know if I go through, I don't think I need that. Now, let me go now through the table and numerical method in a sense by giving numbers and see what we can come up with. Okay, now again my function is f of x equal to x squared minus 4 over x what? X minus 2, but I wrote it in the product form so that I can see about the interpreting the numerical way to see what I can come up with. Now, I started to the right. I start to go toward 2 from the right side of 2. Exactly same thing will happen if you go toward from the left side of the 2. But when I go, as a matter of fact, that it will be a good homework for a student, for yourself, to do exactly same table to make it, but approach toward 2 from the left-hand side, which means you start from 1.9, then 1.999, then 1.9999, and so on and so forth, and make the chart like that, table like that, and see exactly same thing comes up. Okay, now my x, I started with 2.1, then I start to approach toward 2 from right side. So next selection I make for the value of x was 2.01, and next one I selected for the value of x was 2.001, and then 2.0001, then 2.00001, and then 2.000001, and so on and so forth. But I went up to about 6 zeros or 5 zeros, including the decimal to be 6 zeros, and see what kind of behavior my function will give me. So when I end up with, when I give 2.1, I end up with my x squared minus 4 ends up to be 0.41. A square of this one. 2.1 squared is 0.41. Excuse me, 2.4 squared minus 4. So I square this one, then I subtract 4 from that, and I end up with 0.41. And then I also do the same thing here. My selection of my x is 2.1. I subtract 2 from that. Is that right? It's a little bit larger than 2. You see, the answer will be positive. So the answer ends up to be 0.1. And when I multiply this together, I end up with 4. You see that? I end up with 4.1 almost, but let's say 4. Fascinating, is it not? Now I go for the second one to see happen. So second one, I get my point closer to 2, which means I select 2.01. Then 2.01, and what do I do for that? I square it, I subtract 4 from that, and I end up with this answer, 0.0401. You see that, huh? And then I do the same thing for x minus 2. What do? I subtract from 2.01, I subtract 2, and I end up with what? I end up with 1 over 100, the difference. The difference between 2.01 and 2. It's very clear, that one is kind of trivial. So it's 1 over 100. The other one will be 1 over 1,000, 1 over 10,000 when you subtract from that. This column of the data is really explicit. Okay, so I do the same thing with the rest of them, and each time I do, when I come to the f of x, which is what? The product of what? The product of this and 1 over this, which means the product of these two columns, I end up to be 4, 4, 4, 4, 4, 4. So that immediately opens my eyes and say, hey, my kind of intuition. That is in fact a good example to say that sometimes our intuition is not trusted. Intuition sometimes can fail us. You see, twice it failed us. If one time we end up with a 0 over 0, and the other one we end up with a 0 times 1, 0 times infinity, and both of them end up to be not correct. So the limit of f of x as x approaches 2 equals to 4. Isn't that fascinating? So we learn two things from this observation. Number one, don't always trust your intuition, but it's a fascinating way to do. Intuition most of the time helps, not always. And second one is with 1 or 2 examples, do not give up. Try more and more to see what if you can come with different kind of answer. Okay, now let me put this one and see, just repeat what I've said one more time, but in a writing. So here we end up this, we wanted to take the limit of what? X squared minus 4 over x minus 2. So we wrote it in the product form. I repeat myself again. 2 over 3 or 2/3 is same as 2 times 1/3. So is these are absolutely same. But when I did that and I went through the chart, etc., I end up the limit to be 4. And that immediately we notice that limit of f of x over g of x is not equal to limit of f of x over limit of g of x. That's what we hear, and most of the students, they miss the last part of it most of the time. When you say what is the limit of quotient, it's the quotient of limit. But we just saw it, that could not be true. Limit of a quotient is quotient of limit provided the limit of the denominator of the quotient is not 0. Again, because I can put myself into the shoes of the student, I know how they think. So they always, when you ask them what is limit of quotient, there's a quotient of the limit, and they miss the part that is what? That the limit of the denominator must not be 0. So the limit of this quotient is not equal to the quotient of the limit, because the limit of the denominator as x approaches to 2 equals to what? Equal to 0. That is fantastic. That's what we found out from making a little bit mistake. Okay, now let's go to the next one, if I may. Well, this one I have already mentioned, so I just put it there in case if you want to write it, it doesn't hurt. I go over it one more time. Now, if limit of f of x equal to 0 and limit of g of x equal to infinity, then limit of f of x times g of x may not be 0. 0 times infinity, first of all, is not defined, but limit of the product may not be equal to 0 or not defined. Then limit of f of x times g of x may not be also infinity. So it's not 0, it's not infinity, but the limit of f of x times g of x can be a real number, and in this case we tried and end up to be number 4. All right, this is just repetition, I already mentioned it really, if you like to write it. Now we go to algebraic manipulation and see what we can come with the same problem algebraically. So what we do in algebraically, we factor the numerator, which is x minus 2 times x plus 2, then students are very quick to cancel. So we cancel x minus 2 and x minus 2, and we end up to x plus 2. But because mathematics is a very meticulous subject, f of x, this x squared minus 4 over x minus 2 is not equal to x plus 2. So don't jump to the conclusion too quickly. That's what you have to always contemplate, think and reflect, and always be critical in your approach and thinking. Always, in a sense, be pessimistic. Could it be the case or not? Now, let's make two functions out of them. If f of x equal to this, and g of x equal what we wrote x plus 2, these two functions are not same. Are not same in what sense? In a sense that this function f of x, 2 is not in its domain. 2 is not in its domain. Where this function g of x, 2 is in its domain. So this contains all the real numbers, the domain of that, whereas this one contains all real numbers except 2. So what we can do, we can use algebraic manipulation for this problem, and then use g of x instead of f of x, because the graph are same except at one point. So we sketch the graph of this form, and when we finish, we take the 2 on the x-axis, and f of 2, in this case will be g of 2, and g of 2, which is 4, and we put a hole in that. So the graph of this one will be a straight line with a slope of 1, hit the y-axis as 2, and at x equal to 2, g of x equal to 4, so the point 2 comma 4, we make a hole in there. So let me see if I have done it. Yes, I have in fact. Fantastic. So I go through the graph of that, you can see that. Again, I repeat one more time, myself one more time, and these two f of x and g of x are not really same as far as the meticulous subject of mathematics is concerned. So what we do, we go and sketch the graph of g of x because they differ in only one point, and after we finish the graph of that, then we take the part that this one has a hole, this does not have. This has a cut at the point 2, 4, but this does not. So after we finish the graph of that, we make a hole in there. So that's what I have done, and I'm going to put it up for you. So as you can see, this graph with the hole is the graph of g of x. And at 2, 4, at this point, I put a hole there, which means that because the intention is to sketch the graph of f of x, not g of x. So that will be the graph of f of x equal to x squared minus 4 over x minus 2 as what? As x approaches to 2. So the limit of that, if you approach 2 from right, that we did in the chart, in the table we made, or from left will be same, from left and right, the limit will be 4. Again, 2 is not going to ever be reached because it's not in the domain of that, and 4 is not going to be reached because 4 is not also go, it is in the codomain, it is a real number, it is on the y-axis, but in this case will not be in the range of that. So we can say the function is not what? It's not an onto. There is one point in the codomain or in the range that the function is not going to hit it. Okay, let me see. I have another example just for the sake of the argument. I give it to you, and that will be the final. Now, this example is, I have a function that is defined in 3 pieces. One of them is the function is 2x when x is greater than 3, is 9 when x equals to 3, and equal to, again, 2x when x is less than 3. So for x greater than 3 and for less than 3, the function is same. You can see is 2x. So we go ahead and sketch the graph of the function f of x equal to x, which has a slope of 2 and pass through the origin. And after that, we see that as x approaches 3, as x approaches to 3, the value of the function is not 9, definitely. The value of function is 6. You can see 3, when we approach to 3 from the right side, is 6. When we approach to 3 from the left side, is 6. So the limit is 6, but the function is not what? The value of the function at 3 is not 6. The value of the function at 3 equals to 9. And there is a lot of application like that in the applied mathematics. In almost everywhere you can see that. The value of function may not be defined at some certain point, but the function has a different value at that point, at the limit point. Okay then, I hope that this, I'm going to have more examples. And as I already mentioned, the intention is to seek for the motive behind the definition, abstract definition of delta epsilon definition of the limit, and try to somehow melt away the abstraction and come up that the definition will be extremely sweet and beautiful at the end. Okay, then I'm going to now to go through another example, and I don't know, 2 or 3 more examples I'll go through so that we can build up our intuition about the subject of limit, so that then when we go to the abstract, rigorous mathematical definition of limit, we have some good, strong background. We have a kind of intuitively we know what that means, and that makes it a lot easier to comprehend the abstract definition. Okay, then I thank you for watching, and please watch the previous, if you haven't done it yet, previous lecture, and also the lectures that are going to follow. Okay, then thank you again for watching and have a pleasant day, and please stay safe. So long.